Good morning, friends. I welcome you all for today's session. So, in today's session, we'll be starting with numericals on thick cylinder. So, I have noted one problem for you. Let me start with today's session. A thick cylinder with internal diameter 80 mm and external diameter 120 mm is subjected to an external pressure of 40 kilonewton per meter square when the internal pressure is 120 kilonewton per meter square. Calculate the stress, circumferential stress at external and internal surfaces of the cylinder, and also plot the variation of circumferential stress and radial pressure on the thickness of the cylinder. Right, so this is the first variety of problem which we find in thick cylinders. So it is relatively easy. It is just simplification part which we need to do it here and represent it. That is, the variation should be represented along the thickness of the cylinder. So let me start with the solution part. So let us start with the solution part. Now here what he has given is a thick cylinder with an internal diameter of, so the internal diameter di, sometimes it is taken with a capital Di, both are same. So that is, internal diameter is 80 mm, external diameter is d naught, so it is 120 mm, right? And external pressure is P naught, which is 40 into 10 raised to 3 Newton per meter square, and internal pressure Pi is 120 kilonewton. So kilonewton I am writing it as 10 raised to 3 Newton per meter square, right? So these are the things known to us. Now if you just follow your Lamè's theorem, there I have used the terms xi and x naught, which are nothing but the radius. So if I want to calculate xi, it will be half of this, because x is the radius. When the diameter is 80 mm, xi will be 40 mm and x naught will be 60 mm, because these two are the radius and these are the diameters. Radius is half of the diameter. Right? So these are the basic things which we require before we start with the problem. Now I'll be starting with the problem. I'll be using the Lamè's equation. So from Lamè's equations, you need to write the Lamè's equation first. So Lamè's equation gives us the value of pressure at a distance of x from the center. So it is b divided by x square, minus a. So this you can take it as equation 1, and it also gives me the value of sigma c at the value of b divided by x square plus a. So this you can take it as equation number 2. Right, so these are the values, of sigma c and px, sigma c and px. So now I'll be using the boundary conditions for equation 1. So what you can write here is, using boundary conditions in equation 1, we get. So what is my equation 1? Equation 1 is this. What boundary condition I'll be using? So first boundary condition will be, at x naught is equal to 60 mm, P naught will be 40 into 10 raised to 3 Newton per mm square. So this will be my first boundary condition. Right, so value of x naught and p naught both are known. X naught is also known, P naught is also known. So I'll put that value in equation number 1. So what I'll be getting? P naught will be equal to B divided by X naught square, X naught square minus A. B divided by X naught square minus A. So I'll just slightly modify this. So value of P naught is known. It is 40 into 10 raised to 3 is equal to B value is unknown divided by X naught. Okay, so X naught is in mm, whereas pressure is in meters. Here I have made a mistake. So this is in meter square. Right? It is in meter square. So I have written it wrongly. Pardon. So it is Newton per meter square. So where X naught is in mm, so you need to convert it into meter. So it is 60 into 10 raised to minus 3, the whole square, minus A, minus A. So this you can take it as equation number 3. Equation number 3. Now I'll be applying another boundary condition for same equation 1. Okay, so applying the second boundary condition. So second boundary condition is at xi is equal to 40 mm, pi should be equal to 120 into 10 raised to 3 Newton per meter square. So once again you put these values in equation 1. If you put the values in equation 1, I'll be getting 120 into 10 raised to 3 is equal to B divided by 40 into 10 raised to minus 3 square minus A. Right, so this you take it as equation number 4. So now we need to solve these two equations, that is equation 3 and equation 4. So my equation 3 is on the previous page. So just to make things easier, I'll just rewrite that equation 3 on this page. We know that from equation 3, from equation 3, so what I know is 40 into 10 raised to 3 is equal to B divided by 60 into 10 raised to minus 3 square minus A. Right, so this is from equation number 3. So now I'll be solving these two equations simultaneously in my calculators. So let me clear the mode. Okay, then I go to the equation mode. Say equation mode. Next, the number of unknowns are 2. You say 2. So let me say this is my equation 1 and this is my equation 2. Right, so value of a1, I'll put this value. So this value is how much? 1 divided by 40 into 10 raised to minus 3 square. Value of b1 is minus 1. Value of c1 is 120 into 10 raised to 3. Next value of a2 is this value, 1 divided by 60 into 10 raised to minus 3 square. Value of b2 is minus 1, that is coefficient of this, and value of c2 is 40 into 10 raised to 3. 40 into 10 raised to 3. So value of b is, first point is b, so whatever I'll be getting here will be the value of b. So value of b is 230.4. So solving equations 3 and 4, we get, so solving equations 3 and 4, what we get is value of b is coming out to be 230.4 and value of a is 24,000. value of A is 24,000, right? Now substitute the values of A and B in equation 2, right? So in equation 2, what I have listed previously, you need to substitute the values of A and B. So if you are substituting the values of A and B, what I'll be getting, sigma C will be equal to value of B is 230.4 divided by x square plus 24,000. Okay, so once again I'll be applying boundary conditions here. So what are the boundary conditions? At x is equal to xi, sigma C will be sigma Ci, right? So what happens, sigma Ci, that is circumferential stress on the inner part of the cylinder, will be equal to 230.4 divided by xi square plus 24,000. So if you just further simplify 230.4, what is the value of xi? Value of xi is 40, so it is 40 square plus 24,000. So therefore value of Ci, just check out what will be the value. So it is 230.4 divided by 40 square plus 24,000. Now here once again I need to be careful. Why I need to be careful here is sigma Ci should be in Newton per meter square, because pressure is in Newton per meter square. Pressure given to me is in Newton per meter square. So this 40 is in mm. This xi 40 is in mm. So I want to convert it into meter. So what I need to do here is 40 into 10 raised to minus 3. So that is what I have committed a mistake. So I'll be writing one more step here, 230.4 divided by, this is in meters, right? So this is in meters, so this should be in meters, but by default what I have got it in the problem is in mm. So mm, if I want to convert it into meters, so it is 40 into 10 raised to minus 3 square plus 24,000. So be careful, please don't commit a mistake. These silly things matter a lot, else entire problem will be wrong. So it is 230.4 divided by 40 into 10 raised to minus 3 square plus 24,000. So it is 168 into 10 raised to 3. So therefore sigma Ci is 168 into 10 raised to 3. I'll write it as kilonewton per meter square. Kilonewton per meter square, right? Now similarly I'll be substituting another boundary condition in the same equation. So at x is equal to x naught, sigma C will be equal to sigma C naught. So the next boundary condition is at x is equal to x naught, sigma C should be written as sigma C naught. And so if I substitute the values in the equation, I'll be getting sigma C naught will be equal to 230.4 divided by x naught square plus 24,000, right? So you know the value of x naught, substitute that. So sigma C naught is 230.4 divided by x naught value is 60 mm. So it is 60 into 10 raised to minus 3 into, sorry, it's not into, it's plus 24,000. Right? So if you substitute this and simplify, so let me check out what will be the value. So it is 230.4 divided by 60 into 10 raised to minus 3 square plus 24,000. So it is 88 into 10 raised to 3, that is 88 kilonewton per meter square. Therefore, the value of sigma C naught is 88 kilonewton per meter square. So now you need to show the variation. So in order to show the variation, I'll be showing the sector of the cylinder. Sector is nothing but a part of the cylinder. So let me draw the part of the cylinder. So I'll write it here. Variation of circumferential stress and radial pressure is, so variation of circumferential stress and radial pressure is shown below. Okay, so what I'll do, okay, now to show the variation, so variation of circumferential stress and radial pressure is shown below. What I have taken this sector or part of the cylinder. So the radius is somewhere over here. From this point, the center, I have just taken the cut section apart. Right. So this is the inner radius from this point, and this is the outer radius. So I have taken just a segment of the cylinder. Now I'll be first marking the circumferential stresses. So circumferential stresses are 168 and 88. 168 and 88. So I'll just mark it over here. So 168, on the inner side it is 168. So this is the inner surface. Right? So this is the inner surface. So I'll just write here I. This is the outer surface. So I'll just write here O. On the inner surface, the circumferential stress sigma Ci is 168. So let me write it here and mark it somewhere over here. So I'll take some one point over here and I'll call it as sigma Ci is equal to 168 kilonewton per meter square. Right? Now sigma Ci is 168 and sigma Co, that is on the outer surface, what is the circumferential stress? It is 88 kilonewton per meter square. So this is the outer surface. So I'll just mark it here. So here this is sigma C naught, 88 kilonewton per meter square. Similarly, I'll mark out the radial pressures. The internal radial pressure Pi, Pi and P naught. So that is important. Pi and P naught. So Pi is 120 and P naught is 40. Pi is 120. So I'll just mark it somewhere over here. Pi is 120. So I'll mark it here. So this is Pi is 120 kilonewton per meter square and P naught is 40. So this is the outer surface. So P naught is 40. So let me mark it here. So this is P naught is 40 kilonewton per meter square. So in order to show the variation, what I'll do, I'll just join these 2 points. Right. Now the variation is something like this. Right. So also I need to join these two. Right, and you can join these two as well. Right, so this is the variation of circumferential stress along the thickness, and this is the variation of radial pressure along the thickness. Right, so that's it for today's session. Have a great day. Take care. Bye bye.